All right, good afternoon, everybody. We are now deep in our study of duality. We showed strong duality. Right. I gave a physics proof for strong duality, and then last time you watched a recorded lecture which filled in the mathematics behind that physics proof. Right? And then I took you through the sort of cookbook for how you take the dual of a linear program where you have constraints, you have a mixture of inequalities, upper bounds, lower bounds, equalities, and where you have variables that can be non-negative, non-positive, or unrestricted in sign. And we wrote up this whole table of mappings where you take, actually maybe I should put that up again, at least in shorthand. So where's my dual table? Because we're going to use it again today. So let me just write it up again quickly. So the primal is, we sort of decide to call the minimization problem the primal and the maximization problem the dual. Which one you call the primal and which one you call the dual is sort of arbitrary. So we just make that arbitrary decision. And then for the primal, we have constraints, which can be lower bounds, upper bounds, or equality constraints. And we also have variables, which can be restricted non-negative, or restricted non-positive, or unrestricted, right? And what we know is that every constraint in the primal problem corresponds to a variable in the dual problem. And if the constraint is the sort of natural direction of constraint, right? If in the primal problem you have a minimization problem, so it's sort of natural to imagine lower bounds on the minimization problem, greater than or equals. And in that case, you end up with the corresponding variable being non-negative, right? And this comes straight out of the physics proof, right? That when the constraint is set up so that the force is working again, so that the constraint is limiting the movement of the ball, right? The force is non-negative from that constraint. It doesn't pull, right? But if you've negated the constraint to turn it into a upper bound constraint, then you end up also negating the variable and having it be non-positive instead of non-negative. An equality constraint, right, says the ball has to be stuck to the hyperplane. In that case, the force can go in either direction, depending on which way the ball is trying to move. The hyperplane forces it not to move. And conversely, right, with the primal variables, you end up with dual constraints. And a non-negative variable corresponds to a constraint that's going in the proper direction for a maximization problem, right? If you're trying to maximize, then your natural constraints are upper bounds. On the other hand, if the variables are negative variables, then you get lower bounds. And if the variable is unrestricted in sign, that turns into an equality constraint. So this is the duality cookbook table that you saw in your recording, right? We also use strong duality to argue that, at least for linear programming, finding the optimum is completely equivalent to the problem of just finding a feasible point, right? Which is one of the sort of shocking things about linear programming, right? In all of these other problems we've looked at, just finding a feasible solution has generally been easy, right? It's optimizing that's hard. But strong duality tells us that just finding a feasible solution is, in general, just as hard as optimizing a linear program. Okay? Now I said in general because in specific, there is a real difference between these. There are many linear programs where it is essentially trivial to find a feasible solution, but optimizing them is hard. Okay. Now, what is how can these both be true? How can it be true that in general they're equivalent, but on any specific linear program it's hard? Well, because the demonstration of equivalence requires taking your old linear program and constructing a new linear program, right? And so even if the original linear program was easy to find, even if it was easy to find a feasible point in the original linear program, the construction creates a linear program where it's hard to find a feasible point. Okay? But again, in practice, it's often easy to find a feasible point for your linear program. And indeed, this is a necessary starting point for a bunch of the linear programming algorithms that we're going to be looking at in a little while. Okay? So again, theoretically equivalent, but important differences in practice. Okay? Once we had the cookbook, we started using it. And last time, we looked at the shortest path problem, right? And we looked at taking the dual of the shortest path problem, and we found that the dual of the shortest path problem was sort of the problem of finding one min cost unit of flow from the source to the sink, right? And once you know this, it makes a lot of sense, right? Whatever the shortest path is, that's the cheapest way to send stuff from the source to the sink. So the cost of sending exactly 1 unit of stuff is going to be equal to the length of the shortest path. And so taking the dual just reveals a rather different problem whose solution is the same as the solution to the original problem. And this is quite common in linear programming, and it's a reason that when you're working on an optimization problem, it's often useful to formulate it as a linear program, even if you're not planning to solve it that way, right? Formulating it as a linear program and taking the dual can give you tremendous insight about the problem that leads you to solve it a completely different way. Okay? So even if you're not planning to do linear programming for your work, it's good to understand how to do it for your analytical insight. And so we're going to start off today's lecture by taking another example of that. We're going to look at dualizing the maximum flow problem. Okay. So I'm going to express the maximum flow problem as a linear program. Then we will take the dual, and then we will stare at that dual and see what it tells us about maximum flow. Okay. So in order to formulate the maximum flow problem, in order to make it more elegant, I'm actually going to turn it into a circulation problem. Okay. I'm going to add an edge from the sink back to the source. And I'm going to demand that we want a circulation that maximizes the flow on this T to S edge. Okay? So does everybody see that this is equivalent to the max flow problem? Right? However much flow I can send from S to T, by using this edge, I send it back to S and get a circulation, right? And so the maximum amount that I can send from T to S is the maximum amount of flow I can send from S to T in the first place. Right? Now the advantage of this is that now it's a circulation, it's a much more elegant problem. I don't have any exceptions to the balance constraints, right? I can just require balance everywhere. Okay? So let's think about how we would formulate this as a linear program. So what are the variables going to be? What are the quantities that we want to assign? Yeah?
This flow
on every edge, right? So let's write XUV for the flow on edge UV. Okay, so if that's the case, what is our objective function? Yeah.
XTS.
And do we want to, are we going to solve a maximization problem or a minimization problem?
Well, we want to maximize XTS.
Good. So that's our objective. And now, what are the constraints? Yes.
Capacity constraints on each edge.
Good. So how do we write those?
X U V is less than capacity of UV.
Yes, actually, I always forget that I shouldn't use, or sorry. It's a bit of a problem to use U here for a vertex because I'm also using it for capacities, but I don't want to, I need to go back and change my notes, and I haven't, so I'm going to stay consistent with that, and hopefully you'll be able to disambiguate subscripts from regular letters. So yes, the capacity, the flow on edge E has to be at most the capacity of edge E, right? Other constraints on this flow value? Yeah?
For each node, you can say like the flow goes and say X. For every node, you can probably say that for like in edges, X and V, like the sum for the edge inflows, X and V has to equal the sum of
Exactly right. So for every V, exactly as you say, we're going to add up all the flow into V, and we're going to subtract off all the flow. Let me, again, just for consistency with my notes, sum of XVW minus sum of XWV has to be equal to 0, right? Balance constraint. Now there's one more constraint that we usually apply, at least in the net flow, sorry, in the gross flow formulation. Yeah? Yeah, or non-negative, right? So we don't like thinking about negative amounts of flow. Okay. So this is the linear program formulation of Maxwell. Yeah? Everybody sees that, agrees, no questions? Okay. So now we need to think about how to take the dual of this linear programming, of this linear program. So here we have variables and constraints, and we need to think about how to transform those in the dual. So if we want the dual over here, let's see, actually, let me use my, so dual, remember, we call the max problem the dual, so what we're constructing over here is the primal. And the transformation that we see is that each variable in the dual gives us a constraint in the primal. Each constraint in the dual gives us a variable in the primal, right? So you'll notice that we have two different types of constraints over here, right? The capacity constraints and the balance constraints, right? In LP language, we don't think of this as a constraint, right? It's a sign restriction on the variable, so we don't turn this constraint into a variable in the primal, right? But these two we do. So we have two different kinds of constraints, right? And I'm going to use different variables for those different kinds of constraints, right? So we are going to have variables ZV, which correspond to the conservation constraints, the balance constraints, right? There is one balance constraint for each variable V, so there's one variable in the primal for each variable V, right? We also need constraints. We also need variables corresponding to the edge constraints, right? And again, here there's one constraint for each edge. So in the primal, there's going to be a variable for the capacity that corresponds to each capacity constraint in the dual. right? Okay. Now, what kind of constraints are we going to have? And again, just in terms of correspondence, let's not write out the constraint yet, but what constraints do we need to, what set of constraints do we need to think about in correspondence to the dual problem? What do they give us in the primal? Yeah?
A constraint for each forward edge.
Good. So there's a constraint per edge. Right, which corresponds to the variable x of e, right? So some of the dual LP is pretty easy to write down because we know that the objective function, the coefficients of the objective and the right-hand sides of the constraints swap places, right? That's the easy part, right? So what is the objective function going to be in our primal? Where do we find it in the dual that we start with? Actually, at this point, it's sometimes helpful to start thinking about the matrix formulation of the constraints. Okay? So the constraint matrix of this dual, right, is multiplying the vector of variables x sub e, right? And it has various constraints. And what's on the right-hand side of this matrix? What constraint values go into this vector? Yeah?
In this case, the capacities of each edge.
Good. So we've got these constraints, right? So again, just because of order, I'm going to think of the top of the matrix as representing these constraints, and the bottom of the matrix as representing these constraints, right? And so in the top, right, as you said, the constraints that we're going to see over here are the u sub e variables, right? Or sorry, the bounds are going to be the u sub e variables. And what are we going to see at the bottom? Yeah?
0 for the conservation.
Exactly. The bottom of the matrix is going to give us constraints whose bounds are 0. Okay? And now we can actually fill in some details here, right? We know that the upper part is these upper bound constraints, and the lower part has these equality constraints, right? And now finally, what about the quantities that go into this matrix? What are we going to see? So, for example, actually, what are the rows and columns of this? How should we index the rows and columns of this matrix? Okay, so I said over here already, right? This part is going to be indexed by the edges E, right? Each edge is going to give us one constraint at the top of the matrix. The bottom of the matrix is going to be indexed by the vertices V, because we're going to get one constraint for each of the vertices, right? Now, what are the columns going to be indexed by? Yes?
Also the edges E.
Edges, right? Because this is this corresponds to the variables themselves, right? So now we need to understand, like, again, let's start with the capacity constraints. What numbers get put into the matrix to represent these capacity constraints? Yeah? Exactly. The top is an identity matrix, right? Because each constraint deals with just one variable. Okay. What about the bottom? What goes in with, again, we've got a row for each vertex. What goes on that row? Yeah?
One for each edge that goes in, and -1 for each edge that goes out.
Good. So we've got +1s for incoming edges and -1s for outgoing edges. And a whole bunch of zeros elsewhere, right? For the edges that are not incident on the vertex. Okay? So now that we have this matrix picture, we can go back to looking at the primal and thinking about what goes where, right? Everything that shows up in the primal is in this matrix picture somewhere. So where do we find the objective function of the primal by looking at the matrix? Yeah?
It's the vector on the right-hand side.
Right. So the objective of the primal is the bounds of the dual, right? Now we do need to write. We want to write the objective function as a sum over variables. So which variables in the primal go with which of the quantities that we see in this right-hand vector? Actually, easy question first. Is the primal problem a minimization or a maximization? Yeah. Yeah, it's always the opposite of the dual problem, right? So it's a minimization. And now, back to my question, how do we write out the objective function, right? How do we combine these right-hand side coefficients with the appropriate variables? Yeah.
Well, there's E plus V of them, so you should probably put the E of them, the E capacity constraints with the Y sub E's.
Exactly. Remember that we said that for each to each of the capacity constraints over here, we associate a variable Y sub E, and those variables that are associated with the capacity constraints get multiplied by the bounds on the capacity constraints, right? So we have a sum of Y sub E times U sub E. Okay. Now, what coefficients do we put on the Z sub V's? What bounds get associated with those? Trick question, right? What coefficients multiply the Z sub V variables? Yeah? 0, right? Again, the Z sub V variables correspond to the balance constraints, which have bounds of 0. And so you multiply 0 times all the ZVs, so this doesn't even show up in the objective function. Okay. Now, how do we write down the constraints, right? We don't need to write down a lot of constraints because there's just one kind. There's one constraint per edge. So how do we figure out what the constraint is on an edge? There's two things to figure out. There's the function and there's the bound, right? So let's start with the function. Where do we find, for a given, for the constraint associated with edge E, right? Where do we find the coefficients that determine that constraint? Yeah. Exactly, right? So in the dual, the constraints were rows, right? So when we go to the primal, we see the constraints in the columns, okay? And the constraint that's associated with edge E is just, the function is determined by the coefficients of column E. Yes? And so what are the coefficients that we will see in column E? Right? We've already explained how to populate the matrix. So we just need to understand what coefficients we'll see in a particular column. Right? If I start from the top at column E and start, right? I'm going to see a bunch of zeros, right? What's the first non-zero coefficient I'm going to see? Yeah?
There's like a one for the capacity constraint, that's the important portion of the edge.
Right, I'm going to hit the identity, I'm going to hit the diagonal of the identity matrix, right? So I'm going to see a 1. And where is that 1 coming from? It's coming from row E, right? A capacity constraint indexed by E, right? And so that corresponds to the variable that matches that capacity constraint, right? So that's the variable y sub E, right? So you get a 1 times y sub E, right, from the identity matrix, part of this constraint. What other non-zeros show up as we continue down the column? Yeah?
You see 1, 1, and 1 minus 1?
Exactly right. Why do we see a plus 1 and a minus 1?
Because those are the two vertices that are incident on the edge.
Exactly, right? We put plus 1s and minus 1s where an edge is incident on a vertex, right? Now, we got a lot of plus 1s and minus 1s in a single row because a vertex has lots of incident edges, right? But in a single column, each edge is only incident on 2 vertices. It's going into one of them and out of the other one, right? So there's a single plus 1 and a single minus 1. Which variables get the plus 1 and the minus 1? Well, they're the variables that correspond to the constraints where that edge showed up, right? And those constraints are the 2 vertices where the edges were incident. So edge VW gets associated with constraint on V and constraint on W, which means that in the primal, right, this constraint is going to see a coefficient from row V and a coefficient from row W, right? And so if you figure out where the plus 1 and the minus 1 goes, you'll write down plus ZV minus ZW. Okay? So those are the variables that we get out of the matrix. Okay? Now the next question is, will this be, what kind of constraint will this be? Upper bound, lower bound, or equality constraint? And how do you figure that out? Yeah. Good. So again, this constraint, I'm doing this very, very slowly and pedantically because this is the process that you need to go to get practice going through, right? So this constraint corresponds to the variable, the variable x of E, right? The constraint on edge E, the constraint on E corresponds to variable xe. The variable xe is a non-negativity constraint, right? But it's associated with a maximization problem, so it's in the wrong direction, right? And so since it's in the wrong direction, our constraint, I said that backwards. This is a non-negative variable, right? And so it corresponds to a constraint that's in the proper direction, right? Non-negative variables go to proper direction constraints. Proper direction constraints for a minimization problem are lower bounds. So we know this is going to be a greater than or equal to constraint, right? Yes, a question.
Constraint is the direction from E to W. Shouldn't it be ZW minus Z?
Should it be ZW minus Z? Sorry, let me be consistent here. This is going to be YVW. You think it should be ZW minus ZV. Where's our plus one? So here we have a plus one in oh, you think I labeled it wrong rather than, yeah, okay, good, thank you. So yes, it's the outgoing edges that have the plus one and the incoming edges that have the minus one, right? Right, because here, this is incoming to V, so this gets a minus one. It's outgoing from V, so it gets a plus one. Thank you. Okay. All right, so we have a lower bound, and now what goes in the right-hand side? Where do we find the bounds for these constraints? Where do we look? Yeah? We look at the coefficients of the original objective function, right? Max of xts. And what does this tell us that the bounds should be? Exactly. The only non-zero value here is associated with variable ts, which is a particular edge, right? And so similarly, the only non-zero value on the right-hand side is going to be the one associated with constraint on edge ts, right? So 0, right? Except it's greater than or equal to 1 for VW equal TS. For that single edge, it's 1. But for everything else, it's 0. Okay. Now finally, we've given our constraints. What about these y variables and z variables that we've defined? Are they non-negative, non-positive, or unrestricted in sign? So let's ask about the y sub e's first. What should they be and why? And again, what's the process for deciding? If you want to figure out whether y sub e should be, what the sign of ye should be, where do you look? Yeah?
We had x sub e has an upper bound, so y sub e should be greater than or equal to 0.
Good. So in order to understand y sub e, you look at the corresponding constraint, which is the capacity constraint, right? The capacity constraint is an upper bound, which is in the proper direction for a maximization problem. And the variable corresponding to a proper direction constraint is constrained to be non-negative, right? Now, what about the z variables? How do we figure out their sign constraint? Where do we look? Yeah? Exactly. We go back to the conservation constraints that correspond to the z variables. They're equality constraints. That means that the z variables are unrestricted constraints. And now we're done, right? Just by following the cookbook, we created a different linear program whose value is exactly the same as the value of the original linear program. So that didn't require any creative thinking at all. But now comes the creativity where we try to interpret this linear program that we've created as a different kind of perspective on the original problem. Okay? So I think the creative insight starts by looking at these constraints. ZV plus YVW minus ZW is greater than or equal to 0. Does that sort of equation ring a bell? Yeah.
To the price function.
And more generally, right, what is the price function, or what sort of characterizes the price function? Triangle inequality, right? This is a triangle inequality, right? So if we're saying that the y's and z's satisfy some kind of triangle inequality, it suggests that we should be thinking in terms of lengths and distances, right? So we can think of the YVW as lengths and the ZV as distances. And then we have triangle inequalities as the constraints, right? Now we can observe a few extra things about this. First of all, what can I say about YTS? So what should UTS be in the problem as I formulated it? Remember, that's the edge from T back to S. So what capacity am I going to put on that edge when I add it? Yeah?
Infinite.
Infinite, right? I don't want to stop flow from getting, I'm trying to maximize the flow. I don't know what the value is. I'm just going to put an infinite capacity on it. Now, if UTS is infinite, then for any sane answer, YTS is going to have to be 0, because otherwise the value will be infinite, right? And infinity is not going to be the optimum of the original problem. So notice YTS equals 0 since UTS equals infinity. So actually, what does that mean, right? Remember, we had this constraint, this special case constraint when, for the TS edge, and it actually doesn't have a YVW anymore, right? YTS is always going to be 0. So really, the ZTS constraint is simply going to say that ZT minus ZS is greater than or equal to 1. Okay. So if the z's are distances and the y's are lengths, and what is this constraint that ZT minus ZS should be greater than or equal to 1 saying? Well, it's saying that the distance between the source and the sink should be at least 1, right? In fact, you can also notice that the z's in this primal only show up subtracted from each other. So changing them all by the same constant doesn't do anything, right? So in fact, I can subtract z sub s from all of them and just say that z sub s is going to be fixed at 0. Okay? And then zv is just equal to the distance from S to V. Okay. So we have this constraint that says that we want to force T and S to be separated by a distance of at least 1. Okay. These Z's are distances because of the triangle inequality constraints, right? Now, what do we get to choose, right? Again, our goal is to separate T and S. We get to do so by choosing the lengths, right? YVW to create this separation, right? And what lengths do we want to choose? Well, we want to choose lengths that minimize this sum of length times capacity, right? Now, if you think about the sort of the pipes intuition for max flow, right? A capacity is kind of a cross-sectional area, right? How much can go through per unit time is determined by the cross-sectional area of the pipe. So if you take that cross-sectional area and you multiply it by a length of the pipe, what is that giving you? Yeah. The volume of the pipe, right? So we want to pick the lengths to minimize the total volume of the network. Okay. We don't want to put a lot of length on a fat pipe because that creates a lot of volume. Instead, we want to put our long lengths on thin pipes because that won't generate a lot of volume. Okay. So we're already starting to get this alternative perspective for max flow, right? Here we were asking, what's the most flow that you can send per unit time through the network, right? And what we're basically trying to do over here is show that it's possible to separate S from T with a network that has relatively low volume. If you think about it, the volume of the network is what determines how much the stuff can be in the network at a given time, right? So if the volume of the network is very small, it means there's not much stuff in the network at any given time, and that means that there can't be a lot of flow traversing the network. Okay. Let's go a little deeper. Okay. So one thing I'll point out is that this dual LP, which says you want to separate S from T, that actually gives a justification for an algorithm that we developed for max flow, right? What algorithm that we developed for max flow is actually driven by separating S from T? Yeah? And before that, shortest augmenting path, right? So the whole idea of shortest augmenting path in blocking flows is that they aim to separate S and T by a large distance. And that's exactly what the dual linear program is trying to do. And this is not uncommon, okay? These are what you call primal dual algorithms. Which are driven by the structure of the dual problem. And so again, when you're trying to solve a new algorithmic problem, if you're able to formulate it as a linear program, then often taking the dual of that linear program will give you an idea about how to solve about an algorithm for solving the problem. Okay, which is to sort of look at optimizing the dual. Okay. Now let's ask, how would you actually what would be a good idea? What would be a good solution to this problem? Like, what is an example of how you might arrange for T and S to be separated by a distance of at least 1? What lengths might you assign to a network? Okay. Well, one of the easiest things you could imagine doing is assigning a length of 0 and 1. Okay. So if I sort of focus your attention on just assigning zeros and ones, where do you need to assign ones in order to satisfy the constraints of this primal linear program? Remember, we want the distance from S to T to be 1, right? So what does that mean? Yeah?
Assign some edges to be 1, so all factors S to T have at least an edge of.
Good. If I want to make the distance from S to T to be at least 1, I need to put 1 unit of length on every path from S to T, right? And if we focus on the 0, 1 case, right, I need to have an edge of length 1 on every path from S to T. If I want something like that, right, every path from S to T has to cross an edge of length 1. What are the edges of length 1 going to be? Yeah? It'll be a cut, right? So one solution to this primal problem is assign 1 to all edges on a cut and 0 to all of the other edges, right? If I put 1 on every cut edge, I've just made the distance from S to T 1, right? Okay, so any cut gives a feasible solution to this primal linear program. What's the best cut to use given my objective function? Right, what's the value of my solution going to be for a given cut? Yeah? It's going to be the capacity of the cut, right? So if I'm trying to optimize, what cut should I use? Yeah? Exactly. Best thing to do here is to use a min cut. Right? Put a 1 on every min cut edge, and that gives you a feasible solution, and the value is equal to the capacity of the minimum cut. Okay. So great. What have we just shown? Right? We have duality here, right? Here we had the maximization. Here we had the minimization problem. What we've just shown is that the maximum flow value that you can achieve in the original problem is less than the minimum cut that you can get using the LP dual. Right? Now, have we shown that they're equal? Yeah?
The 0, 1 choice, like, so we made this 0, 1 choice, but it's a pretty good choice. So, non-duality will fit there.
Well, we have to be careful. Yes, it is a good choice, but do we know that yet? It's not clear, right? So what we've said is, here is a solution to the dual problem, and that gives a bound on the primal problem. And of all the candidates, the min cut is the best bound, but the candidates we've restricted to being 0, 1. Maybe there's a fractional solution that gives an even better bound. So far, we've only proven an upper bound a weak duality, right? When you give a specific solution or a choice from a restricted set in the dual, that gives you a bound on the primal, but you don't get a guarantee of equality. Okay. Now, in this case, I'm going to show you in a minute that you can argue equality and recover Maxwell min-cut, but we need a little bit more, machinery, some more definitions in order to make that argument. So let's take a break first.
The first 5 problem sets, we have 25 graders on average, or
5
total so
averaging,
far.
yes. Everybody's eager to resume. A couple of logistical things. First of all, we need a couple more graders for this week. We only have three right now, and we should be averaging 5 just to make sure that everybody gets a chance to grade. Remember, grading is one of the things you get graded on in this class, and if we run out of problems before we run out of graders, then there's going to be some leftover people who are going to have to do some kind of make work, like doing 1,000 push-ups in class or something like that. So, are there a couple more people who can volunteer for this week's grading? Excellent. The two of you, if you can join Michael, or check in with Michael after class, that'll be great. Second logistical thing, I am headed to a workshop tomorrow, and I'll be out on Friday. And I'm disinclined to give you 2 recorded lectures in 1 week. That's a bit much. So my thinking was to cancel class. But if everybody is just loving this material so much and just wants to keep going, then I could put up another recorded lecture so that we just keep moving. And obviously I'll pick up wherever we left off on Monday. So since you're the ones who are here, you get to vote, right? Who would like to sort of keep going with an extra lecture? And I expect the answer to be 0. And who would instead prefer to cancel class? So who votes for an extra recorded lecture this week? Oh my God. All right, well, I'm afraid you're outvoted. So we will, I mean, honestly, you're allowed to say you're having fun and would like to see another lecture, but, this will subtract a little bit from what we cover, obviously, if I cancel. But it seems like most people would like a rest, and that's just fine. All right, yes?
Material that's relevant for the PSETs.
Well, if we don't have it, then I won't put those things on the PSET, right? If we do have it, then it will let me, like, the PSET will have a more dense coverage of what we're doing instead of being spread out over more lectures. Okay, yeah. Oh, so the next lecture will be on algorithms for linear programming, the simplex algorithm and the ellipsoid algorithm. Okay, which are super cool. But of course, you'll get them on Monday if we don't do the Friday lecture. Okay. All right. So let's pick up where we left off. As I said, we've showed this upper bound, but we restricted to 0, 1 solutions. And so maybe there is a better fractional solution, right? A sort of a fractional cut that gives an even better bound on the max flow. Now we know from our previous analysis that that's not true, but I'm going to show you how that comes out for free from linear programming so that you don't need to be clever and prove it directly. And this requires us to introduce another idea of complementary slackness. So this is something that I mentioned in the context of min-cost flow, and now we're going to see it in its full generality in linear programming. So given primal and dual feasible solutions x and y for a linear program and its dual, we are going to define what's called the duality gap to be the difference between the objectives. Okay. And if x is associated with the minimization with the maximization problem, and y is associated with the minimization problem, then, oops, did I just say that backwards? Sorry, wrong way around. X is associated with the min problem, y is associated with the max problem, right? We know that that x and y are bounds on each other. They can't cross through each other. And so the minimization problem is always going to have a value larger than the maximization problem. And so the duality gap is always non-negative, right? We also know that at opt, the duality gap is 0, right? And in fact, the opt is somewhere inside the duality gap, right? It's between the upper and lower bounds that we found from our specific solutions, from our feasible solutions, okay? And so in fact, this duality gap measures how far both solutions are from opt. Right? So the two bounds sort of provide comparisons to each other. Right? If they're very close together, then you know that both of them are close to the optimum solution. Okay? Now let's rewrite So if we assume our sort of standard form, canonical form structure that we're used to for linear programs, let's rewrite the standard form, the dual form LP. Basically, we're going to turn it into a kind of standard form. So maximize YB, and again, the canonical form says YA should be less than or equal to C, but I'm going to introduce slack variables. So we've already seen slack variables in the primal problem, in the standard form, right? I'm just adding them into the canonical form as well, okay? And now notice that our duality gap, Cx minus Yb, right? In our, right, we've said Ya plus S is equal to C, so I'll plug that in to Cx, right? And then I'll subtract off Yb, right? But again, in our standard form, what is Ax equal to? B, right? So this can be written as Yax plus Sx minus Yb, but Ax is equal to B in standard form, right? So our duality gap can be taken, is equal to a dot product between the primal variables and the dual slacks. Okay? Now, another thing to notice or to remember is that in our standard form LP, all of these x variables are constrained to be greater than or equal to 0, right? We've also constrained all of the slacks to be greater than or equal to 0. Okay. So if this duality gap is 0, if we're at optimum, what does that tell us about these non-negative S and X variables? How can we get 0? Yeah?
Every non-zero primal variable must have 0 slackness.
Exactly, right? The only way to get 0 out of a sum of non-negative terms is for every individual term to be 0, right? So what we need is that for every I, Si times Xi has to be equal to 0. And the only way that can happen is if at least one of Si and Xi is 0. Okay? And what we've just argued is known as the complementary slackness condition. Complementary slackness condition says that feasible x and y are optimal if and only if for every I, one of xi and si, which is yai minus c, is 0. Okay. In other words, either the primal variable is 0 or the dual constraint is tight. And that's the complementary slackness condition. And it's useful in both directions, right? You can use the complementary slackness condition to prove optimality. Yes, a question?
T minus y instead of y minus c. I mean, if there's a...
Oh, sure. I mean, it's 0, so it doesn't matter, but thank you. Okay. So you can use complementary slackness to conclude optimality, right? If this condition holds, you're optimal. The duality gap is 0. But more importantly, you can often use the fact that you're optimal to conclude that complementary slackness holds, and from that infer interesting things about your solutions. Okay, and that's what we're going to do now. Okay. Also notice that this goes in both directions, right? At optimality, either a primal variable is 0 or the dual constraint is tight, and the other way. At optimality, either a dual variable is 0 or the corresponding primal constraint is tight. Okay. And again, I phrased this in terms of standard and canonical forms, but it's true for any form, for any form of linear program, right? You can generalize this. So let's see how to use that. So let's apply this to max flow. Okay, so let's consider some optimal x and y for these two, for the max flow linear program and its dual. We also had z variables, right? X is in the primal and y's and z's in the dual. Okay. Now I'm going to define a cut. It's going to be the set of vertices V whose distance is strictly less than 1. Okay. It's a set of vertices, so it's a cut. I claim it's actually an ST cut. Why is it an ST cut? Yeah. Right. Zs equals 0, and Zt is greater than or equal to 1. So S is in the set, T is not in the set. Okay. Now, suppose that edge VW leaves the cut. In other words, ZV is in the cut, and ZW, or sorry, that V is in the cut, and W is not. Okay? What can we conclude about that? Well, that means that ZV is less than 1, and ZW is greater than or equal to 1. Right? But now if we go back to the edge constraint, right, we have this triangle inequality constraint here, right? So from that, we can conclude that YVW plus ZV minus ZW is greater, right? That's the constraint that we had, right? And so, but what we have here is that what this tells us is that YVW is at least ZW minus ZV, right? And we've just said that ZW is at least 1 and ZV is smaller than 1. That means that their difference is greater than 0, right? Not greater than or equal, but strictly greater than 0. Okay? So we have just shown that a variable is not 0. What does complementary slackness tell us? Yes?
The constraint in the opposite column 0.
Right. Complementary slackness tells us that the corresponding constraint is tight. What is the corresponding constraint? Yeah? Capacity constraint, right? In other words, xVW, right, the corresponding variable, is equal to UVW. So what is that saying in words? If the edge is leaving the cut, then it's saturated, right? All right, let's look at the other direction, literally. Suppose that YVW enters the cut, or that edge VW enters the cut. What does that tell us? Well, just by definition, that tells us that ZV is greater than or equal to 1, and ZW is less than 1. Right? Now we also know that YVW is greater than or equal to 0. Right? That's one of the constraints that we have. So that tells us, if we put these two things together, that ZV plus YVW, right? ZV is already bigger than 1, and then we add something non-negative to it, that's certainly going to be bigger than ZW. Okay? If we rewrite that the obvious way, right? YVW plus ZV minus ZW is greater than 0. What is that saying in the language of complementary slackness? Yes.
Was 0.
So yes, but what step did you skip in order to say that?
The dual constraint is tight. Is not tight.
Right. This is loose or slack, right? And that tells us that the corresponding variable, and what is that corresponding variable?
The flow.
Right. So to this constraint, we correspond the variable xVW, and it has to be 0 at optimality. And what is that saying in English? Yeah?
Avoid that edge.
Right. That edge is empty. Right. In summary, in any optimal solution, okay, all exiting edges are saturated. All entering edges are empty for this particular cut, which tells us that the value of the flow is equal to the value of this cut that I defined. And so we have indeed recovered max flow min cut, right? By defining a by looking at the optimum and defining a cut, right? Complementary slackness tells us that the value of that cut is equal to the value of the flow at optimum. and therefore that max flow is equal to min cut. Or sorry, it directly tells us that there's a cut whose value is equal to the flow value. So the optimum solution can be seen as a cut, it defines a cut and not a fractional. The optimum solution might be fractional, but this procedure defines an actual cut, even if the solution that you start with is fractional. It's called a rounding procedure because you've turned things into integers. Okay. All right. Any questions about that? Let me try and squeeze in one other thing very quickly so that we can start right away with algorithms on Monday. Unless everybody thinks this is so cool that they've changed their minds and want to have lecture on Friday, but I assume not. So we did a whole bunch of stuff with max flow. What if we want to apply the same insights to min cost flow? Okay, and what I'm going to do here is avoid redoing all of the work over here and just ask what changes in this problem formulation if we want a min cost flow formulation instead of a max flow formulation. Right? Down here we already have a bunch of constraints that say, sorry, min cost circulation. Down here we already have a bunch of constraints that say feasible circulation, right? So what do we need to change in order to make it a min cost circulation problem instead of making it a max flow problem? Yeah? Only the objective function, right? What I did here was I basically cheated. I said to do max flow, we're going to do min cost circulation where we have minus infinity on the, or where we have a cost of 1 on the TS edge, or a minus 1, right? So the only change in the min cost circulation problem is to the objective. Now instead of just XTS, it turns into a sum of C sub E times X sub E. Okay? Same constraints as before, no change. Now, if that's the only change in the starting linear program, what does that change in the dual? If we're changing the objective function in the primal, what are we changing in the dual? Yes?
Constraints.
Exactly. Right? In the original problem, we had a bunch of 0 bounds on the dual constraints, right? Now they're going to be CE bounds. So now I can just go ahead and write down the dual. It's the same objective function because we didn't change the bounds in the primal problem, right? So we get the same objective. But now our constraint is that YUV should be less than or equal to, our constraint are that ZV minus ZW plus YVW should be less than or equal to CVW instead of 0. That's the only change. Okay. One other change. We switched from a maximization problem, because we're trying to do max flow, into a minimization problem, right? So we switched the direction of the objective. What does switching the direction of the objective in the primal do to the dual? Yeah?
Objective for the dual.
That's one of the things that it does, right? Our dual was a minimization problem and it becomes a maximization problem, but there's another change that happens when we switch the direction of the objective in the primal. Okay? Before, our constraints were proper direction constraints, right? We were trying to do a max and we had upper bounds. Now, when we make the change, we're doing a min and we have upper bounds. which means that the constraints are in the wrong direction, which means that the variables that were previously allowed to be non-negative now become non-positive variables. Okay? So now, as you dig through this program, you discover that all of the ZVs sort of have the wrong sign for understanding what's going on. I'm just going to define PV to be minus ZV. I'm just going to negate those variables. Okay? And so this lets me rewrite the constraints. Right? Now this is PW minus PV instead of ZV minus PW. And I'm going to move it to the other side and write this as YVW less than or equal to CVW plus PV minus PW. And we also have that YVW is less than or equal to 0. Okay? Now, what's this quantity? Thinking back to our min-cost flow analysis. Right, this showed up when we were solving min-cost flow. Yeah?
The reduced cost.
This is the reduced costs. Okay. So what this is saying is we want to come up with prices, right? And once we have prices, this gives us reduced costs. And, right, the only bound on each YVW is the reduced cost of edge VW. So this is basically going to be equal to the reduced cost. But we also have this constraint that Y should be non-negative. So this is equal to the reduced cost if negative, and 0 otherwise, right? If the reduced cost is positive, then the tight constraint for Y is just that it's not allowed to be bigger than 0. Okay? And now our objective function is just trying to add up, the negative parts of the reduced costs, or it's adding the negative reduced costs multiplied by the capacities. Okay. And now we can again invoke complementary slackness and see what it gives us. Okay. If we have an edge that is not saturated, okay, then complementary slackness tells us that the corresponding dual variable, YVW, is equal to 0. Now, if YVW is equal to 0, that becomes a constraint on the reduced cost, right? So that tells us that the reduced cost, CVW with P, is not allowed to be negative. Okay. Or to put it in another way, if the reduced cost is negative, then the edge has to be saturated, which is exactly what we got from complementary slackness studying min-cost flows, but now we get it for free without having to identify it. On the other hand, if the reduced cost of the edge is positive, okay, then the constraint, or the reduced cost constraint, on YVW is slack. Okay, because this quantity over here is non-negative, but Y is not allowed to be non-negative. So this constraint will be slack. Now, if this constraint is slack, then the corresponding variable, xvw, must be 0. So what is this telling us that we already knew about min-cost flows? Well, it's telling us that if the reduced cost is if the reduced cost is positive, then the edge is empty. Right? So these are exactly the reduced cost criteria that we figured out directly for min-cost flows, and we get them for free by looking at complementary slackness for linear programming. So essentially, if I had taught you linear programming first, I could have skipped like 5 or 6 lectures, right? But then I would have had to think of something else to lecture on. So I think it's better this way, right? All right, any final questions? So on Monday, after you've had a nice, relaxing Friday weekend, we will start looking at how you solve linear programs. What are the algorithms for them? Okay, I'll see you then.